So this is lecture number 11 on stochastic process. Today's lecture on queuing chain. So what is queuing chain? So chain means is a stochastic process with countable countable means x1 x2 sequence of random variables. So we know stochastic process is a collection of random variables. Collection of our index set. Index set must be ordered or partial order. But here we take the index set as a natural number. So that is called a chain. If the index set is a natural number or non-negative integers, then we say it is a chain. So like Markov chain, queuing chain, like that. So what is queuing chain? So consider a service facility. So consider a service facility in some shop or on some online thing or in internet or in any other queue or in a ticket counter. So consider a service facility such as a checkout counter like supermarket, checkout counter or maybe ticket counter at a supermarket. Now suppose that if there are any customer waiting for service at the beginning, of any given period, at any period, say period from starting from 9 to 10 a.m. starting at 9. So at the beginnings, any customer waiting for that. Customer may came before that. So start from 9. Customer came 5 minutes before or maybe whatever. So a given period of some unit time. Unit time may be 1 minute or 1 hour, whatever. 1 unit time. Exactly one customer, say exactly one customer will be served during that time. So take it as a 1 minute. So every minute there is a one customer, or maybe it's a ticket counter. It may be say 5 seconds. So every 5 seconds there is a one ticket is issued. So that unit may be 5 seconds, and that during that period. And that if there are no customer, customer waiting for service. If there are no customer, no service will be provided. At the beginning, of a period, none will be served. So this is important. This is actually real. In real life, this is not happening. Not happen. So what is this? So none will be served. So this is important assumption, but non-realistic. So during that, so like that, say 1 minute is needed for every customer. So it starts at say 9, and at 9 they say there are three customers. So after 3 minutes, they all will be served and they will go. They just check out. So at say 9 minutes, 9 and 3 minutes, and say there is no customer. Now say at 9 minutes sorry, 9 at 3 minutes 30 seconds, there is one customer. They came at the customer came in the counter at 9 past 3 minutes 30 seconds. But the assumption is, okay, you have to wait for 9:04, up to 9:04, because there is a 1 unit, and since there is at the beginning there is no customer, the whole time, whole 1 minute will be there is no service. So if at 9 at 9 a.m. 3 minutes and 9:03, if there is no customer, then the next customer will be served at, if there is some, will be start at 9:04. So if some customer came at say 9 and 3 minutes, say 45 seconds, and another customer has 47 seconds, and another customer say 9:03 at 58 seconds, three customer is there, still there is no service. Once is 9:04, then one customer is served. That is why this assumption, to make it simple basically. So 1 unit is just, is no starting, there is no, just that next unit no service. For it is actually for simplicity, but really it is more complicated in real life at that period. This is the assumption. Now let zeta n denotes the, which is a random variable, denotes the number of new customers arriving during that time, during the nth period. So it is xi n at the nth period. So nth minute or something. It's nth unit. After nth unit. So, no, it is nth unit. Now we assume that we start from x0. So at 9 it is x0, 9:1 it is x1, 9:2 it is x2, right? So we assume that one more assumption is that we assume that zeta 1, zeta 2, that's xi 1, xi 2, these are IID. We also assume that these are IID. So number of customer came, that is independent. So what customer came at 9, that customer came at 5, 9 and 3 or 9 and 4, that is independent, and also IID, not only independent, IID. Actually, it is not true. In rail counter or in any counter, some rush hour is there. So in rush hour, the density is high, and there is some density low hour is maybe at a night or at a very morning. There is a small number of that, so that density actually not equal. But we are assuming that for simplicity, that's IID. Okay, so these are IID, and the PMF is taken as safe. It is PMF because the number of so it is discrete random variable. So with PMF, probability mass function is f. Now starting, say it is x0. So let x0 denote the, so xi is the number of new customer, and x is the that number of customer in the queue. So x0 denote the number of, let's start at 9, say number of customer present initially. So starting at initially how many, x0 many. So it is again, it's a random variable. Now what is xn? Let xn denotes the number of customer present at, so starting is a zero period. So after one unit time is the first period 1. So customer present at the end of the nth period. Oh, no. At the end of the nth period. So if xn is 0, then xn plus 1 is xi n plus 1, right? Because at the nth period, after the end of the nth period, right? Say it is start at say uh, 9 a.m. and say it is end the first period end at 9 and 1 1 past 9. So that means that it is the end of the first period, and your x0 is initially said is say 3 or 0. Initially it is 0. That after that will be 0. Then it is a xi n. So how many xi n is the number of nth customer is the nth period. So it is xi was if n equal to 0, right? You put n equal to 0. That means your x0 is 0. So initially it is 0. Your x1 is xi1, right? Because what is x1? X1 is the number of customer present at the end of the nth period. So this is the idea. So this is your say 0, and this is your the 1 unit time. And in that period xi n many, so n is 0 here. So xi n plus 1. So xi 1 many customer came in this period. So that means now it is x1. So x1 is actually xi1. X1 is the number of customer present at the end of the nth period. So end of the first period. So xi. Similarly, if somewhere if say xn is 0, now there is no customer service served. Now in that period now it is a n plus 1th period. So at n plus 1th period, xi n plus 1 customer came, and so xn plus 1 is actually equal to xi n plus 1. And if it is not 0, and if xn is not 0, xn is greater than equal to 1, then what happened? Clearly then xn plus 1 is xn plus xi n plus 1 minus 1. So one person is served, so it's check out. So xn is the number of initial that starting period, start at nth period. There are n many start at not n, start at n plus 1th. So here it is xn means at the starting at n plus 1th unit. At the end of the nth unit, that is the starting of the n plus 1th unit, it is xn. So xn is say 5. Then say xi n plus 1 many, say 7 many came new customers. So it 12 minus 1. The 1 is served. So this is the recurrence relation of the stochastic that random variables. Now xn is a Markov chain. Now then xn is a Markov chain. Why this xn is a Markov chain? It is clear. Actually, it does not depends on once you xn is given. It does not depends on xn plus 1. So xn plus 1 does not depend on xn minus 1. So probability of some xn plus 1 say 7 is given that xn is say 5. It does not depends on the xn minus 1 xn minus. It depends on the xi n plus 1. Does not depends on the xn minus 1, or it depends on xn also and xi n plus 1. So, but not depends on the xn minus 1. It is the Markov chain. So state space, what is state space? State space is non-negative integers. Natural number union 0 may be a state because there are no customer, then it is 0. And what is a transition matrix? And transition functions or transition matrix is P is given by what? The probability point from 0 to y is just f of y. So that means starting it is 0 and end it is y. That means y many customer came, new customer, no will be served because at the starting it is 0. So it is just f of y, and for other value x, where x is greater than equal to 1, that is what. So that means from x to y means it is there x many customer is there previously. How many new customer came? Is it y minus x? No, it is not y minus x. It is y minus x plus 1. So y minus x plus 1 many new customer came. There already X customer is there. So the Y plus 1, but one customer is served. So that's why it is Y. So this is F of this. So what is the probability of that? This is F of this. F is the PMF, the mass function of this each value. So this is a basic transition matrix or transition function for queuing chain. So this is very important. So this is the, and once I have this Markov chain with this transition matrix, we know how to find this initial distribution and the joint distribution and the limiting distributions, and whether it is steady state or stationary distribution or not, we can easily find that. We need to find that transition matrix or the transition probability. Now, one more chain is a branching chain. That is also very important chain in genetics or any chemical reaction. The branching chain is very, very important. So now we're going to in the branching chain. So what is branching chain? So again, it's a chain, means it is a stochastic process with x1, x2, xn, or x0, x1, x2, xn. Maybe non-negative integers or maybe natural numbers. Actually, we in more conventional we take x0, x1, xn, and dot dot dot. Now consider a part. What is branching chain? So consider a particle. Now it is a particle, or maybe gene, some, or maybe something, some bacteria or whatever. Particles such as some neutron, maybe neutron, or maybe bacteria, such as some neutron, or maybe so bacterium, such that or maybe some gene that generate, or maybe some colony, some rabbit or whatever. So that generate new particle. So it generates a new particle. So it may be some animals or some tree. It generates some new tree or new animals. So new particles. We call it as particle of the same type. It will be the same type. So that means if it is a mango tree, then it is the new particle means a new mango tree. The initial set of object is initial set of objects. It may be human beings. Objects is referred as, is sometimes called as referred to as belonging to the zeroth generation. It's called zeroth generation. So start with the zeroth generation. So there are 2 rabbits in a colony, or 4 rabbits in a colony, and this is called zeroth generation. Now, what is the next generation, or is the first generation? Is actually the child of this. Or if it is the electron in an atomic reactor, the starting neutron is the zeroth generation, and is break into 3, then 3 first generation neutron. So it is a graph structure actually. A typical situation is this. And typical situation is what? As follows. So like that picture may be like graph. So it is like a graph means not a graph of function. It is a graph theory invented by Euler. So it is a zero generation. Say there is only one element, maybe several elements. Generation, and then it's say break into the two particle, or 2 is break into the, say there is amoeba is break into the 2. Now this is called the first generation. These 2 elements or living objects called first generation. So here it is x0 equal to 1 and it is x1 equal to 2. So it is break. It's not, there is not a new birth, it is a break, it's 1 2, or maybe new birth and that the previous particle just abolished. And then in the first generation there is maybe may not be in 2. If it is 2, they call binary tree. Maybe the 3, and maybe 1, maybe 1. the second generation. And maybe some this structure follows this, and maybe there is no such new object from this, maybe. And this going on the third generation. So it is x2 equal to say 4, and then again x3 equal to 2 is reduced. So this is like a tree. It's called tree in graph theory. It's called tree. So going on, and at the last stage, it is just a 2, and then it is break into again 2, and this is into the 1. So it is the nth generation, and this is the next one is the n plus 1 generation. Whatever is in it, then the next one is n plus 1. Now, what is xn? We define xn, n greater than or equal to 0, denote the number of particle in the nth generation. So number of particles in the nth generation is called xn. We denote xn. Now, various particle, different particle, various particles in a generation. In a generation, there are maybe more than one. So various particles in some generation may not give rise to a new particle. So here it is a particle which have no next generation particle. Sometimes is called that next generation particle is called child, and the previous generation is called say parent. And the particles from the same parent is called sibling. These are the terms: sibling, parents, and child. So this and this are sibling. This and this, but this one is and this one is the same generation but not sibling. So it's a new particle. New particles. So may not give some new particle. Just completely vanishes. At a given time, what happened? At a given time, say t, particle from the several generation may coexist. So particle from several generation may coexist. So there may be this is a real situation. For amoeba or other thing, it is not a situation. Once amoeba break into two amoeba, that previous amoeba actually vanishes. It's changed to the new. But for a mankind or any other rabbit, the parents and child is exist in the same time. So it's called coexist. So remember that xn is the number of element in the nth generation. It is not that the nth generation of the previous generation. So if there is a start with say 2 element, say 2 parents, and it's like we can say the one particle is called say one couple. So one couple means one particle. So we start with the one couple means one particle, and say it's created two particle, and then still that the previous thing 0 generation is exist. Now there are three particle with one generation 2 particle and 0 generation 1 particle. So generation may coexist. Now suppose that, so we have this is our assumption. Real life situation that this is more complicated, but suppose that it is a more simpler case. Suppose that each particle give rise to xi particle. So xi is a random variable in the next generation. So it may be 0, it may be 1, there is no child, there is some probability with no child, no with probability 1, there is some, so with probability 0.3, one child, with probability is a 0.4, with her 4 child, like that. In the next generation, where the xi is a non-negative, it cannot be negative, there cannot be -1 many child, non-negative integer valued random variable. Now density is take as f, so having density f is a density. So density here means is a mass function, quality mass function. Density we referred in for discrete case, we also write density. Quality mass function is a density in discrete case. Now that's also called offspring. That is called offspring. The child also called offspring. Number of offspring of the various particle is independent. That's an important assumption, that various particles are independent. That means if there are say 2 couples, so number of child from the first couple is independent with the number of child of the second couple. That is a realistic. So how many new offspring is generated from the a particle is, that does depend on the how many generate from the other particle. Number of offsprings these are independent. Now then, what is the important thing? Zero is the important part. Is zero is an absorbing state. So if it is 0, everything vanishes. So there is no such new thing, and it's 0. And there, if once it is 0, is for a whole life it is 0, whole time it is 0. So once it is 0, its probability 0. From 0 is 1. From 0 it can be 1. 0 is the absorbing state. And what is the other probability transition matrix? The probability of starting from is from x to going to y. So what is the meaning of that? Is x going to y? So that means at the nth generation there is x many particle. Now the first particle say gives xi1 many offspring, second particle gives xi2 many offspring, dot dot dot, and there are x particles, so xi x many particle, and that is must be y. That is equal to, and that's we have to find the probability of this. So remember, this is interesting and some complicated situation where xi1, xi2, xi(x) is a random variable and x is also a random variable. That's the important thing, important part. So the index is also random. So that is the important thing. That is the most important part. It is like a conditional thing, say conditional part. So sometimes we call x1, x2, x3, 3 random. But now it is a x1, x2, xn, and where xn is also a random variable. So what value of n we don't know. That is also n with n equal to 1 with probability something, n equal to 5 with probability something, some probability, positive probability. So it is a very complicated situation. Is you need a conditional thing for that. So you need first you have to take condition on that random index random variable. So this is the thing, probability of xi1, xi2, xix equal to 1. And how do you find that? You know what is the, we assume that x1, xi1, xi2, xix is independent. We have to also assume that x is independent with this. That xi1, xi2, xix is independent with the x also. That so where that xi1, xi2. So it's condition x given for a given x. X's are IIT with density, that means mass function f. So what is the probability from 1 to y? So it is just a one is single element gives rise to the y many child, that means what is the probability of that is the f of y. F of y is the density set. So number of child came from a single particle. So that is the fy. So this is the total get of or structure of this branching chain. And next one is a very important chain, which is called birth and death chain. And we stop with this birth or death chain, and then next class we find the stationary distribution of this all this chain, and this unphased chain, and this modified unphased chain, and what is the recurrent state, and what is the transient state of this chains, that we find in the next video. We just discuss now uh, the last chain, that last important chain is called birth and death chain. This is also very important chain, birth and death chain. So birth and death chain. So birth and death chain. What is birth and death chain? Our birth and death chain, the state space is 0, 1, 2 up to dot d, or maybe infinite, some 0, 1, 2 dot 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 dot. In that case, we consider d as infinity. D is infinity means is not actually up to infinity, it is just non-negative integers. Infinity actually there is no number infinity, it is just a notation. Yeah, d equal to infinity means 0 is all non-negative integers. Now in birth and death chain, what happens? It is start from x to y. It is goes to with probability qx. It goes to y equal to x minus 1. That is a it is a death. That is a qx. If y equal to x plus 1, it's a new birth. It's a px. And y equal to x, there is no birth, no death. It is called rx. So obviously px plus rx plus qx is actually equal to 1 for all x in step s. So this is the important thing. And obviously px and qx, we assume that this is a positive. Rx may be 0, but qx px must be positive. Otherwise, if it is no birth, no death, it's not interesting because you can't say birth and death chain. But in the one thing is this: if d is not infinity, d is finite. Finite something like d less than infinity. It's not that d less than infinity. It's like infinity is a number, d is a number, so d is less than infinity. That's not the case. The case is d is finite. So d is any natural number, or better I say, d belongs to some natural number. That is a better, more mathematical. So now that PD is 0. That means there is a P is the D is the stop. The absorb no, not observing. You can't go beyond that. So you don't have any D plus 1 minute. So D once it's 0, no new birth. And obviously, if it's 0, there is no death. So this is also 0. And if D is infinite, then Q0 is 0, but PD may not be 0. So this is called path and death chain. We go into the details of this, of the stationary distribution, whether it is exist or not, or there is a limiting distribution. What is the limiting distributions, and what are the chain is recurrent or not, and for what value of Q or RS if the chain is recurrent or chain is transient, and what are the different closed subset of that, or any irreducible subset or not. For this birth and death chain, for branching chain, queuing chain, and the unphased chain, these 4 important chain we discuss. For this 4th chain, 4 special type of Markov chain, and the recurrent, what are the recurrent standard, what are the transient standard, what is the irreducible closed set, and for which value of px and for which value of rx we have these conditions. These are discussed in the next thing, next video. And these are we go into details on that, and that will be the end of this Markov chain syllabus.